Hello everyone, welcome back. This is going to be another video in the Theory of Computation series titled Prerequisite Graph Theory. Okay, so you are expected to know a little bit about graph theory going into the course, okay? And everything you need to know, I'm going to sort of talk about in this video. A lot of it is very definition based. There's not much heavy maths going on. It's just sort of like, do you know what a directed graph is, what an undirected graph is? And then we'll talk about, how we can sort of describe graphs using sets, subgraphs, paths, simple paths, trees, cycles, and stuff like that, basically. So just as long as you sort of, the main idea with this video is just sort of making sure that you're familiar with those terms. And we'll also talk about how you can actually use graphs to also represent things like relations, okay, which is kind of interesting as well. So like binary relations specifically. So like the if you watched the last video, we spoke about the beats relation. So for like a game of rock paper scissors, and we'll talk about that again towards the end of this video. But anyway, without any further ado, let's get straight into this. Okay. So first things first is what is a graph, right? So a graph, no, sorry, let me write it like this. A graph, or you can call it an undirected graph. So, if you want to be specific, it really is an undirected graph, or at least what I'm talking about here is just an undirected graph. So a graph or an undirected graph, it's effectively a set of points with lines connecting some of the points, basically. So with lines connecting some of the points. This has me finish. Okay. So to put it really simply, that is basically what a graph is. About graph theory, it's just a set of points with lines connecting some of the points. And whenever I say some of the points, I mean it's really what I mean is that it's really up to your discretion how many of the points are connected by lines. Okay, so maybe all of the points are connected by lines. Maybe some of them are connected by lines. Maybe none of them are connected by lines. Completely up to you. Okay. Okay. Right. So now that we have sort of the basic definition down, let's be a bit more specific about what we mean. So obviously there are sort of two components of any graph, and that's sort of the points that are connected by our lines and the lines connecting those points. So those are the two main components, and we give those components special names. So the points, I'll give an example of a graph in a second as well, but let's just get through this terminology first. So the points are called nodes, and you might see some people call them vertices. So if you're familiar with geometry, then that's the term that's used there quite heavily as well. And the lines that connect some of the points are called edges. Okay. So yeah, nodes or vertices for the points and edges for the lines, effectively. Okay. Right. So now we have that terminology down, here's an example of a graph. So you might have something like this. So you're gonna have. So what we do first is we sort of introduce however many nodes you want. So in this case, I'm going to introduce 5. So we're going to do 1, 2, 3, 4, 5, like so. And then you can label them. And obviously labeling is arbitrary. Okay. So I could label this 1. I could label this 2, 3, 4, 5, or you could label it any other sort of choice that you want, right? But just assign a different number to each of the nodes, and then connect them however you want. So in this case, I'm going to connect them sort of like this. So 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, and 5 is connected to 1. And that gives us sort of like this this sort of star shape, right? And this is a valid graph. And what you'll notice is that not all points are connected, because 1 is not connected to 4. Okay? So 1 is not connected to 4, 4 is not connected to 2, 2 is not connected to 5, 5, 3, and 3, 1. And yeah, and so therefore, not every single node has to have an edge. And not every single pair of nodes needs to have an edge between it. Okay, it's up to you how many edges you have in your graph. Okay, and so I should label this as an example of a graph. So this is a graph or an undirected graph. Okay, they're the same thing for our purposes. Right, and so it's also useful to define something called the degree of a node. So all that means is basically the number of edges at a particular node is said to be the degree of that node. Okay, so if I were to look, for example, at the graph on the left, okay, then you can see here that there is, at 1, there are sort of 2 edges, right? So the edge coming in from 2 and the edge coming in from 5. So at 1, we say there are 2 edges, okay? And so therefore, the node labeled 1 is of degree 2. Similarly, the node labeled 4 is of degree 2, node labeled 2 is of degree 2. So basically, all of the nodes here are of degree 2, okay? So we can note that. So all nodes here have degree 2. And so this notion of degree is just something useful that we decide to introduce. In terms of, today, it's just sort of us introducing it. But I'm sure later on there'll be sort of reason for us introducing this as a definition. And just within graph theory itself, it's a useful thing to have. So all nodes have degree 2. Okay? And another thing that we say is that between any two nodes, no more than one edge is allowed. Okay? So no more than one edge is allowed between any two nodes. So between any two nodes. Okay? So for example, if I go up to my graph here and I consider nodes 3 and 2, I'm only allowed to have one edge between them. Okay, I can't have some other squiggly line that sort of goes over here like that. Okay, I can't have two paths effectively from 2 to 3 or 3 to 2 because there's no direction. Those are the same thing. Okay. Okay, so I'm only allowed to have one edge connecting those two nodes. All right, and that's true for all pairs of nodes. Okay. So yeah, between any pair of nodes, I'm only allowed to have one edge connecting them. Okay, and just to avoid sort of weird stuff, we typically denote that with a straight line. Okay, but you can obviously do whatever you want. You can make it squiggled. You can, as long as it sort of doesn't, just don't make it too weird. Don't make it like cross itself or do weird stuff, right? Yeah, I mean, I don't necessarily know if there's a rule that prevents it from crossing itself, but I wouldn't do that, right? Like, typically we use straight lines. Just don't overcomplicate it if you don't need to. Okay, so this is the rule that we have, that no more than one edge is allowed between any two nodes. Although, so even though that's not allowed, what we do sometimes allow is we sometimes allow an edge from a node to itself. And so we call that a self-loop. So we may allow an edge from a node to itself called a self-loop. Okay, so in our graph up here we have no self loops, but I can easily add one in by just sort of taking the node number 5. I know it's a little bit like a 3, so let me fix that. The 5, and just sort of attaching a loop around it like this, right? And then that's a self node, right? So that's basically, sometimes we allow sort of that edge from a node to itself, and we call that a self node. That's basically it. It just basically is an edge starting at 5, going around in whatever loop you want. You could do this sort of this and then end at 5. Okay, and that's fine. Okay, so now being a little bit more specific about things, we say that in a graph G, so if I were to just sort of label my graph capital G, in a graph capital G containing two nodes, so it may have more than two nodes, but specifically it must contain these two nodes. So containing nodes I and J, we actually say that the ordered pair IJ represents the edge connecting I and J. Okay. And another thing to note, before I sort of talk about that, is that in an undirected graph, which is just the type of graph that we've been looking at so far, in an undirected graph, the order of I and J doesn't matter. Okay, and what I mean by that is effectively the edge connecting I and J is the same as the edge connecting J and I, right? Because we're only allowing one edge between those two nodes, and so if I say that the ordered pair IJ represents the edge connecting I and J, that's the same as the edge connecting J and I. So even though the notation is different, right? Because ordered pairs do care about order, so there's two different ordered pairs, but they mean the same thing, right? So in an undirected graph, the order of I and J doesn't matter, since the edge connecting I and J is the same as the edge connecting J and I. Okay? And so, thus, the ordered pairs IJ and JI represent the same edge. Effectively. And so for that reason, we actually, sometimes use sets instead of ordered pairs to talk about this notion of sort of the edge, sort of describe the edge connecting two nodes. So like, we also sometimes use sets or unordered pairs. So we also sometimes describe undirected edges using unordered pairs or sets, as in sort of, so if we wanted to say the edge connecting I and j, you might just write it as the set containing the elements I and j, right? So this is an equivalent notation in terms of like, some people might use sets instead of ordered pairs for undirected graphs. So when we're talking about undirected graphs, obviously we've already said that we're only allowing one edge between any two nodes. And so for that purpose, obviously the edge connecting the node I to the node j is the same as the edge connecting the node j to the node I. So actually, if we were to represent that edge with an ordered pair, then the ordered pair ij is obviously different to the ordered pair containing the elements ji in different orders, because the order doesn't matter, but they're actually saying the same thing. So it might be more convenient for us to use a set instead, because the order doesn't matter. So even if I flip j and I around, it won't actually change the edge that I'm talking about, right? Just from the explanation that I've already given. And in a set, the order doesn't matter. So swapping those elements around doesn't change anything, which is exactly what we want. So in a sense, for me anyway, it makes more sense to use sets for undirected edges anyway. Okay. Right. So now that we have that down, we can move on. And we're going to say let V be the set of nodes. Okay, and so you might ask, how can we actually have a set of nodes? And it's a fair question. Ultimately, to each node, we obviously just assign a number, as we've done with the graph over here. And then in our set, we just basically list the numbers. So a very common practice is just to say, if I have, let's say, 7 nodes, I'll assign numbers 1 to 7, different numbers from 1 to 7, different integers from 1 to 7 to each of the nodes. Okay, and then put those in a set, and that's my set of nodes effectively. Okay, so let V be the set of nodes of my graph capital G. Okay, and let E be the set of edges. So obviously the set of edges is actually going to be a set of sets. Okay, because obviously if we're using sets to describe sort of the edge between node I and node J, then the set of all edges will be a set of a set of sets effectively, because each set of sets, or each set within the set is going to represent the edge between node I and node J. Okay, so it's a bit funky, but it's how we do it. And I'll give an example as well, so hopefully that makes sense. And let E be the set of edges. Okay, then we say that effectively capital G is equal to this ordered pair with the set with this ordered pair. So the first element of the ordered pair is a set of nodes, and this is the set of edges. Okay, so we can actually describe our graph using this ordered pair notation. So the first sort of component of our ordered pair will be the set of nodes, and the second component will be the set of edges. Okay, so if I have a graph G with some specific nodes V, and if I have a graph G, I can basically talk about talk about that graph in terms of sets, right? Because for any graph, there are two main components that we need to identify it, and that's the set of nodes and the set of edges. Once we have those two things, actually we don't even need a picture of the graph, because remember, even though I could change, so for example, for this graph over here, right? We'll do an example where we classify it in a second, but just sort of thinking about it, we don't even need this picture to really understand what's going on. If I just give you the set of nodes, so just numbers from 1 to 5, and I give you which two nodes are connected, right? So for example, I might have for the edge set, I might say that, okay, node 1 is connected to node 2, node 4 to 5, 3 to 2, so on and so forth. If I give you that, then you should be able to draw a picture using that information. So it's enough actually to identify the graph without even drawing it. So instead of drawing it and then identifying it, you can actually identify it and then draw it, kind of thing, using this process. So that's why this is useful, because it's just sort of basically just another way of showing that pretty much everything in maths comes down to set theory, right? So ultimately, these graphs, even though they are pictorial, we introduce them sort of pictorially, like I'm giving you a picture before showing you this set representation. Effectively, at its fundamental level, it's just a set. It's just like it's just a pair of sets, right? So one of those sets is the set of nodes, and the other is the set of edges, and that fundamentally will always be able to describe any graph using that information. Okay, so what we mean when we say G is equal to this sort of ordered pair is we're just saying the graph G, right, is defined by the set of nodes and the set of its edges, effectively. So the set of its nodes, the set of its edges. Okay, so, and as I've already said, there are two ways of describing a graph. So we can describe a graph with a diagram, or more formally, by specifying V and E. Okay, and obviously V and E, there's a set of nodes and a set of edges. Okay, so what we can do is we can either draw a diagram to show which graph we're talking about, as I did at the very beginning, or we can actually use this sort of set notation to describe it. And then we should be able, once we have one of those, we can find the other one anyway, right? We can construct it. But yeah, okay, that's just fundamentally what's going on. Okay. Okay, so I just need to add another box. Right, so now let's actually go through one of these formal descriptions, because I said I would. Ultimately, so if we go back to the first graph that I sort of drew, so this sort of star-shaped graph, how would we describe that? Well, we can say for the earlier graph, we have that, and I'll label it capital G. So capital G is equal to, so it's going to be an ordered pair, right? And the first element of that ordered pair will be the set of the nodes, okay? And so our nodes, I number them from 1 to 5, so, and it's common practice to do that, right? And so the set of nodes will just be the set containing the sort of first 5 natural numbers, or the first 5 positive integers, okay? So that's my set of nodes there, the set containing the elements 1, 2, 3, 4, and 5. Okay, obviously you can interchange those, doesn't matter, or set order of elements in the set is irrelevant, as I'm sure hopefully you guys know. If not, check out my prerequisite video on sets. And then obviously we also need to have the set of edges, and that is a little bit more nuanced, but you can do it as a set, and we'll just stick to the ordered pair notation here. So we'll say that edge node 1 is connected to node 2, node 2 is connected to node 3, node 3 is connected to node 4, node 4 is connected to node 5, and node 5 is connected to node 1. Okay, so that's how you would basically read that. And obviously I could have, instead of node 5 connected to node 1, I could have put node 1 is connected to node 5, node 5 is connected to node 4, because obviously those two things, they mean the same thing, even though the notation is slightly different. Okay, so that's that set, and then we have to end off the ordered pair because we started it over here effectively, right? So we have to finish it over here. Right, so that's one way. That's the set way of defining a graph. Okay, and so I have my 5 nodes. So I look at this. If you wanted to go from this to the picture, you look at the first thing. You look at the set of nodes. So you have 5 nodes labeled 1 to 5. So let's do them like this: 1, 2, 3, 4, 5. Okay, right, and then you have that 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, and 5 is connected to 1. Okay. And then this is actually the same graph, okay, as we started off with, except what you'll notice is that what we started off with is effectively just I've moved around the points whilst keeping the strings attached, the edges attached to the pairs of nodes. I've just moved them around because what I've done is I moved, instead of doing 1, 2, 3, 4, 5 sort of in a circle, I moved 4 over here, right? I moved 4 over here, 2 down over here, 3 down over here, but the connection is the same. Effectively, all I've done is I've unwinded the connection here, okay? So this is actually the same, okay? So another important thing though is also realizing when 2 graphs you have are the same. But that's not necessarily something that we need to go through in this video, ultimately. But it's just something, I guess, to be aware of, that you can have 2 graphs that look different, but are actually the same. Okay, and so what's going to happen is if I were to move this number 3 up here, this number 2 down here, this number 4 up here, and where do we put number 5? Like down here? Then I'll get that star shape, hopefully, right? But that's that. I mean, you can try that out for yourself. Okay, one of the questions that I'm sure a lot of people normally think, with any maths, or at least relatively pure maths, is what really is the applications of this? Okay, to an extent, like there's many applications of graph theory. I'm not going to go through all of them. I'm going to skim the surface, but obviously we've labeled in this case the nodes of our graph using sort of natural numbers. But actually, we can, instead of obviously numbers are a form of information, right? But they don't really mean anything other than just a label effectively for nodes in this case. But we could arbitrarily, instead of numbers labeling nodes, we could have cities labeling nodes, and then sort of somehow convey information through the edges. So actually, graphs are frequently used to sort of convey, to represent data, right? So graphs are frequently used to represent data, okay? So, as I was saying, if we were to use graphs to represent data, then what you might see is that nodes represent, things like cities, right? Nodes, I should say, nodes might represent cities. So nodes might be cities, and edges, highways between those cities, right? Or something else that you might see is nodes being people, right? Or nodes could be people, and actually the edges could be friendships. And so any result that we prove about graphs, really, keeping it general here, is actually directly, could be directly translated to some model, like, for example, a group of friends, right? Because obviously each of the friends we could represent with nodes, and the friendship ties we could represent with edges. And so actually you get some quite interesting stuff going on in terms of those sort of dynamics, and some interesting results which you might not have realized just from, analyzing the pure side of graph theory, and then sort of taking that to a like a real life model, like one where maybe the nodes represent cities and the edges highways, or nodes could be people, and it just could be friendships, right? So there is actually some use in this in these sort of pure mathematical fields, and there will be use as well in the theory of computation, okay? And sort of delving into a little bit how you might see graphs being used. Okay. And we say that so any graph with nodes labeled, and so whenever we say nodes labeled, we mean like without like the typical numbering that we use. So with nodes labeled and or edges labeled, is said to be a labeled graph. Okay, is a labeled graph. Okay, so one example of this might be a graph where maybe we have nodes being cities, as I said. So like let's say sort of we have this. So we have Ithaca. Don't know if that's how I say it, but that's what the textbook used. We also have Oswego. I don't know what these cities are, but I assume they're American. San Francisco. I do know what that is. San Francisco. Right, and then you might have something like Boston over here, and then you might have like New York over here, right? And then effectively, so our nodes are just cities. Sorry, I know it's like sort of a bit tight at the bottom of the box there. I should probably expand that. That's okay. And then we have edges between them. So my graph might have an edge between Ithaca and New York and San Francisco and Boston and New York. So those are my edges. So this is my graph. And Oswego here doesn't actually have any edges at it, effectively. No edges coming towards it from anything. I'd say coming towards it, obviously they're not pointing towards it, but hopefully you see what I mean. But that's okay, right? It's still a valid node in our graph, so it's still a valid graph even though there are no edges at this specific node. Okay. And maybe in this case, the example that the book used, effectively the edges are actually labeled with effectively the cost of the cheapest sort of non-stop flight between sort of two cities is labeled effectively on the edge connecting those two cities. So for example, between Ithaca and New York, it might be calculated to be sort of 98, and I think it's dollars. So $98 is the cheapest flight, if it were possible to fly non-stop between two cities, and the cheapest possible sort of price you'd have to pay for that flight is $98, right? Or I'm not sure if that's 100% true, but you can imagine that this could be used to sort of model a situation like that, okay? And then you might ask the question like, okay, what is the sort of cheapest way for me to get from, Boston to Ithaca, right? And then you would sort of add up sort of, or you'd be able to figure out what that would be if you have sort of all the possibilities labeled on a graph and numbers attached or weights really attached to the edges. You'd be able to add up the different paths and see which path gives you the minimal price, something like that, right? So you can see how like this can extend application. So maybe the cheapest non-stop flight between New York and San Francisco is $378 if it's possible to fly non-stop. Boston, San Francisco, $378 again, and $169 between Boston and New York. Okay, so if I were to go from Boston to Ithaca by going to San Francisco, then New York, and then Ithaca, that's obviously much more expensive if I were to fly non-stop than from Boston to Ithaca, right? Stopping at New York. Assuming that this is all the possible ways to do that, which I'm not sure if it is. Probably isn't, but I'm not sure. And so like this is the type of thing that you might see in terms of like an application of graphs, and textbook wanted to make that clear, so I thought I would also talk about that. Okay, right. So sort of back to the pure stuff. Okay, so yeah, back to the nitty gritty. So obviously for sets we have a notion of a subset. Okay, so we have an idea of what a subset of a set is. So capital A could be a subset of capital B if all the elements in A are in B, effectively. Okay. And that was just our definition for subset. We can also define things called subgraphs of a particular graph. Okay, so we say that effectively a graph capital G is a subgraph of graph capital H, or so another defined graph capital H, if the nodes of G are a subset, right? Because remember, the nodes effectively can be described using a set. So this just boils down to the definition of a subset, effectively. So the nodes of G are a subset of the nodes of H, right? And the edges of G are the edges of H on the corresponding nodes. Okay, so so it's a little bit confusing, but ultimately, let's look at an example with a different sort of graph. So let's define a graph, which I'll do this pictorially, so with a diagram, which has say 6 nodes. So you can have 1, 2, 3, 4, 5, 6, and let's connect the nodes as follows. So they're going to be connected on their outer perimeter, like that, forming a hexagon, and we're going to have these sort of special connections here, just sort of an arbitrary diagram. Here, connection, no. Try and keep it a straight line. Here. Okay, I think that's fine. So this is just some graph. Obviously, we also need to label our vertices, so you might do it in sort of, you might go around clockwise. So that's 1, that's 2, that's 3, that's 4, that's 5, and that's 6. Okay, now this is a graph. Okay, obviously, so far by our definition, what we've been looking at so far, this is a graph. And then a subgraph of this graph might be something like this. So you take the vertices 1, 2, 3, and 5, and you take these specific connections between those vertices like that. And then effectively, we say that graph G in red is a subgraph of graph H, which is just the entire graph. Okay. And the reason for that, okay, going back to the definition here to make sure we're confident with that, is that effectively all of the nodes in G, effectively, so nodes 1, 2, 3, and 5, are also nodes in the graph capital H. So effectively, the set of nodes of G is a subset of a set of nodes of H, because all the nodes in G are in H, effectively, or all the nodes in that set are in the set of all the nodes in H. Okay, so we have that condition, so that's true. And then we need to look at the second condition, which is that the edges of G are the edges of H on the corresponding nodes. Okay, so for example, you might say something like so obviously you have to look for that at the set of edges. So in this case, with our specific labeling, you might have these sort of 1 is connected to 2, 2 is connected to 3, 1 is connected to 3, and 1 is connected to 5, something like that. So that's your set of edges in this case for the subgraph. And obviously, if you look at the entire graph, these edges are also present. Hey guys, sorry, I just wanted to add this in to the video. So when we're talking about subgraphs, right, obviously in the video, what I used is I used a specific example with 6 vertices. So we have 1, 2, 3, 4, 5, 6, and we labeled them clockwise. So 1, 2, 3, 4, 5, 6, as so, and then we connected them like this. So 1 to 2, 2 to 3, 3 to 4, so on and so forth. We did something like this, also like this. We connected 6 to 2, 6 to 3, and 6 to 4. Right. So this was the graph that I had in the video, and I was talking about that being a graph effectively, because if I consider the set of vertices here, well then that would just be the set containing the elements. Sorry, what am I doing? That would just be the set containing the elements 1 to 6 as so, right? So V in this case is just effectively the elements 1 to 6, and E, so the set of edges in this case, is obviously going to be, well, it's going to be quite long, but it'll start out like 1 to 2, so there's an edge from 1 to 2, then an edge from 2 to 3, and so on and so forth, and you just continue it like such, right? And then I was talking about this specific subgraph here, so the subgraph containing the nodes 1, 2, 3, and 5, and these specific edges like such, right? And I'll be able to tell it's a subgraph because when I label my set V, I'm going to label it so the set containing elements 1, 2, in this case 1, 2, 3, and 5, which is a subset of V, right? So the set containing elements 1, 2, 3, 4, 5, and 6, right? So that's the first thing I need to check. The second thing I need to check is that all of my edges are also in the initial graph as well. So if this is my initial graph, and we'll call this G, and this is my subgraph, call it H. To check that it's a subgraph, first of all, we needed to have that V as a subset. So we'll call this V2. This is V1. V2 is a subset of V1. So we're happy in that regard. Then we need to check that E2 is going to be a subset of E1. So those are the two conditions that we need to check. So E2 itself is going to be obviously the set containing the edges, so the ordered pairs 1 to 2, right? 2 to 3, 3 to 1, and also 1 to 5. Okay? And obviously that will be a subset of E1. And so in this case, that will be a subgraph. Right, but another thing that I want to point out, though, is that effectively if we do something like renumber these, so if my initial graph G looks something like this, and then my H actually, instead of using 1, 2, 3, and 5, instead what I do is I use 2, 3, 4, and 1, let's say. So I label this top vertex, this top vertex is 2, this is 3, this is 4, and this is 1. So I just completely scrap the initial ordering. Then what I'll have is in my set V2 will be 1, 2, 3, 4. And that's fine, that's still a subset of V1. But my set E2 will now be 2, 3, right? 3, 4. 2, 1 will still be there, which is the same as 1, 2. So this will be there, this will be there. 3, 4, so I need to add 3, 4 in there. Right? So 3, 4, and I need to change 3, 1 to 4, 2. Okay? Because now that's going to be like my new effective edges that I've created by renumbering, effectively. And in this case, right, 4, 2, you actually won't spot it in this set, right? You will spot 3, 4, but 4, 2 you won't spot in that set because in the initial numbering, this 4 here is not connected to this 2 up here. So there's no edge connecting those two nodes. And so actually that wouldn't be a subgraph, okay? So there is an issue with just renumbering however you want. So whenever you're looking at subgraphs and you want to label it, you use the same sort of, I mean, this is typically done quite obviously, but just be aware that relabeling nodes could cause potential issues with something that looks like a subgraph when I sort of write it out like this and I have 2, 3, 4, 1. It looks like it's on top. It's a part of the larger graph, right, which I call G, right? But actually, by our definition, it isn't, because E2 here is actually not a subset of E1. So you need V2 to be a subset of V1 and E2 to be a subset of E1 for it to be a subgraph. Okay, and when we relabel, we get some problems with that. Even though technically there is a numbering, right, of G, right? I could renumber the vertices of G such that this thing here, this H, is a subgraph. So I could sort of change the edges in G, like renumber it. So this could be 1, 2, 3, 4. This could be 5, and this could be 6, and then relabel all the edges and so on and so forth. So change E1. Then H might be a subgraph, but if I don't do that, then it isn't. Okay. So even though that might be possible, it isn't a subgraph if these two things aren't obeyed. So don't get confused with that, okay? So always just make sure that those two things are obeyed, and if they aren't, then it's not a subgraph, okay? Even if it looks like if there's a way that you could label it such that it fits on top of graph G, right, which there is, it actually isn't a subgraph of graph G because you've changed the labels effectively of your nodes. So that can be a problem that I wanted to point out. And then we also have things called paths, okay? So a path in a graph is effectively a sequence of nodes connected by edges. Okay, so for example, a specific path might just be, this path. So obviously you go from 1 to 2, 2 to 3, 3 to 1, and then 1 to 5, right? That's a path, okay? Yeah, effectively, just any sort of sequence of nodes connected by edges is a specific path. So it could be 4 to 6, 6 to 3, 3 to 4, right? That's a path. You go 4 to 6, 6 to 1, 1 to 2, that's another path. And I mean, obviously, there are lots of paths on the graph. It's effectively just, at its simplest, a sequence of nodes connected by edges. Okay? Right. And we can also use that definition to talk about a simple path, right? So a simple path is effectively just a path that doesn't repeat any nodes. So for example, on the above, it might be something like, okay, starting at 4, going to 6, and then 6 to 1. Okay, that's a path that doesn't repeat any nodes because I'm not going back to 4, I'm not going back to 6 or anything like that, right? So that's a simple path because it doesn't repeat any nodes in the journey, effectively. Whereas if I do something like, okay, 1 to 3, 3 to 2, 2 to 1, that's not a simple path because I've used 1 twice. I've started at 1 and ended at 1. Okay, and then we also have a notion of what it means for a graph to be connected. So we say that a graph is connected if every two nodes, every pair of nodes has a path between them. Okay, so effectively what that's saying is that if I give you two nodes, you'll always be able to somehow get from one node to the other, right? So for example, in this sort of applied sort of graph case, Oswego, this is not connected because there's no way, for example, to get from Oswego to Ithaca. It's not connected at all to the graph. Okay, but for example, if we look at sort of this graph over here, the star, that is connected because if I want to get from 1 to 4, I can go from 1 to 5, then 5 to 4. There is a path between those two, and the same is true for all pairs of nodes on that graph. Effectively, same thing up here, right? So that's what it means for a graph to be connected. So hopefully you have an idea of what these things mean. Okay, right. So moving forward, we can now talk about things called cycles, right? So effectively just quite a lot of definitions here that you should be familiar with. So a path, and if not, well then watch this video. A path, we call a path a cycle if it starts and ends. So if it starts and ends on the same node. So it's a path that starts and ends on the same node, effectively. So for example, in the graph we had over here, if I go from 1 to 3, 3 to 2, then 2 to 1, that is a cycle, right? I mean, it's also a path, but specifically it's a cycle because we started at 1, we ended at 1. But it's not a simple path because it repeats 1, okay? Because it would be a simple path if it didn't repeat any of the nodes. So you go from 1 to 3, 3 to 4, for example, it doesn't repeat any nodes. But in our case, you go 1 to 3, 3 to 2, then 2 to 1, so 1 is repeated twice. Okay, so this is a cycle. And we can also define a simple cycle if we have effectively a cycle that contains a path that contains at least 3 nodes and repeats only the first and last one. So a simple cycle is effectively a path that contains, greater than or equal to 3 nodes, okay, and repeats only the first and last ones, okay? So it doesn't repeat any of the other ones, okay? Whereas for a cycle, it doesn't say that it repeats only the first and last nodes. It says that it repeats the first and last node. Sorry, it's actually the first and last node. I want to say first and last. Well, yeah, I mean, you get what I mean. But effectively, for just a normal cycle, you could repeat, at least by this definition, you could repeat any of the other nodes, right? So you go 1 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 2, 2 to 1, something like that, right? If you wanted to, but then you repeated 2 and you repeated 1, okay? But that's in a cycle, right? Because you started and ended on the same node. But it wouldn't be a simple cycle, even though it has greater than or equal to 3 nodes involved. It's a path that has greater than or equal to 3 nodes. It repeats 2, so it's not a simple cycle. But for example, 1 to 3, 3 to 2, 2 to 1, that is a simple cycle because only 1 is repeated twice, and there's 3 nodes, so that's greater than or equal to 3. 3 is greater than or equal to 3. So that's a simple cycle. Okay, so that's just definition again for you. Okay, right. So a couple more definitions here. We can also define a tree. So we say that a graph. So a graph could be specifically labeled as a tree if it is a connected graph. So if between any two pair of nodes that I give you, you can effectively find a path between those two nodes. So a graph is a tree if it is connected. So there is a way to get between any two nodes on the graph, right? That you want to get to, that you want to sort of find the path between. You can always find that path between any two nodes on the graph. So a graph is a tree if it's connected. So if it's a connected graph, and the second condition is that it has no simple cycles. Okay, so there is no sort of effectively paths that contain more than greater than or equal to 3 nodes and repeat only the first and last node. Okay, right. Okay, and so if you sort of think about it, then you can sort of construct this not too like you could sort of imagine what a tree might look like, right? So if I have sort of these 3 vertices here, I need my tree to be, if I need a graph is going to be a tree if my 3 nodes are connected. So there has to be a way to get from this node to this node, right? Okay, so maybe it could be something like this, right? Similarly, there has to be a way to get from this node to this node, right? So I might think of doing something like this, and then obviously get between this node and this node, I could do something like this, okay? But if I do that, actually I do have a simple cycle though, right? Because if I label this 1, 2, and 3, a simple cycle I could form is 1 to 2, 2 to 3, and then 3 to 1. So actually, to make this a tree, I just remove this edge here, and then you realize that actually this is a tree because I can get from 2 to 3 by going from 2 to 1 and then 1 to 3. Sorry, I can get from 1 to 3, 1 to 2 very easily, and also there's no simple cycle, right? There is just no way I could formulate a simple cycle, right? Okay, and in general, sort of more extensive trees look a little bit like this. So you might have sort of 1 here, 2. Oh, let's just do it like this. So 1, 2, 3, 4, maybe 5, 6, 7, and then something a bit like this. Okay. So yeah, you can check for yourself that this graph that I've just drawn is connected. In other words, you can get between any two nodes that you want to get. There's a way to get from 7 to 5, right? So 7 to 3, 3 to 1, 1 to 2, 2 to 5. So every single pair of nodes there's a path between them. Okay, there exists a path, and there's no simple cycle. There's no way that I could formulate a simple cycle here, right? Because if I wanted a simple cycle like 7 to 3, 3 to 6, I'd also need 6 to 7, but I don't have that. And you can just check for yourself that there are no simple cycles in the entire graph. So this is actually a tree, okay, by definition. So this is a tree example, right? And although we won't really go into the thing I'm about to say today, it's also worth mentioning that sometimes what we can do with trees, so a tree may contain a specially designated node. So it may contain a specially designated node. So basically you just choose one of the nodes and you call that node the root. Designated node called the root. So, for example, I might choose, say, this node down here to be the root, node number 6, or I might choose node number 4 to be the root, or I might choose node number 2 to be the root, or node number 1 to be the root. It's up to me which node I call the root. And for now, it's sort of, this, at least the textbook doesn't really go through any scenario in which, like, the reason why we would do that, but, it's just a choice that comes up and may come up later. I expect it will, they're mentioning it. So just be aware that it's something that we do a little bit in practice is we designate one of the roots and we call it the root. And so you can have things like rooted trees as well. But they don't talk any more about that in the textbook. So just for now, be aware that you can effectively do that thing. You can just designate one of these roots and call them, one of these nodes and call it the root effectively. So 6 could be the root, 2 could be the root, 3 could be the root, whatever. And then, that's pretty much all the textbook mentions about that. Okay. Okay, and the last sort of thing to note here is that any nodes in a tree that are of degree 1 are called the leaves of the tree. Okay, because effectively they're just hanging on the ends, right? So for example, on the tree to the left, 5, 6, and 7, and 4, those are the leaves of the tree, effectively, right? They're just on the end of the tree. They can pull them off. They have only one thing pulling them, one edge pulling them, effectively. If you think about it like that, are called the leaves of the tree. Okay. The only exception is the root. So if one of those leaves was, if one of 4, 5, 6, or 7 was the root, then that wouldn't be a leaf of the tree. That's specifically the root, unless the node is chosen to be the root. Okay, so these are just rules that we have. Okay, so any node in a tree that's of degree 1 is called any nodes in a tree that are of degree 1 are called the leaves of the tree, unless one of those nodes is your root. Okay, so if 4 is the root, then it wouldn't be a leaf of the tree. Right? If it wasn't a root, then it would be a leaf of the tree. So that's really good, the exception to the rule. Right, okay, so now moving forward to the last main definition, we have to talk about a directed graph. So this entire time, we've really been dealing with undirected graphs. Okay, trees are undirected graphs. Paths. We've only really been talking about paths for undirected graphs, right? So that really begs the question: is what is a directed graph? Okay, well, a directed graph effectively has arrows. So obviously, in the graphs we're looking at so far, the way to connect two nodes is via an edge, but there's no center direction, right? So an edge doesn't have sort of an arrow pointing, let's say, from 3 to 7, right? So in a directed graph, we actually have arrows instead of just simple lines that connect two nodes. So it has arrows. A directed graph has arrows instead of lines to connect nodes, right? And we actually, for directed graphs, we do allow more than one effectively edge to be sort of between any two nodes that we choose. Okay. Well, actually, yeah. I mean, in fact, we allow at most two. Okay, so we allow with an undirected graph, we allow only one edge between any two nodes. For a directed graph, we allow at most two. Okay, so effectively, there's also some other terminology. So the number of arrows pointing from a node is called the out degree of that node. Okay, and the number of arrows pointing to a particular node is the in degree. And the number of arrows pointing to a particular node is the in degree. Okay, so we have the out degree, which is like the number of arrows pointing away from a node, and the in degree is the number of arrows pointing into a node. So let's look at an example. Okay, so an example of a directed graph to start off with would be something like this. So we're going to have, let's say that we have 6 nodes. So 1, 2, 3, 4, 5, 6, like so. And we label them as follows. This is 1, 2, 3. Just go clockwise around. So 4, 5, 6. And then, effectively, we have arrows instead of lines between nodes. Okay, so maybe between 1 and 2, we have an arrow pointing from 1 to 2 like this. Then we can have from 2 to 1 an arrow pointing from 2 to 1 like this. Okay, so we do allow, in this case, 2 edges to be, well, really lines or edges. Still edges, are just instead of lines, are just arrows. So in this case, we do actually allow 2 edges between 2 nodes, okay? But we don't allow 3, right? Because there's only 2 ways that, because obviously an arrow either points from 1 to 2 or from 2 to 1. There's no other direction. So at most we can have 2 edges between any 2 nodes, okay? And in this case, we have an arrow pointing from 1 to 2 and an arrow pointing from 2 to 1. You can also have an arrow from 6 to 1, like so, an arrow from maybe 5 to 6, like so, an arrow from 5 to 4, like so, and then an arrow from 6 to 3, like so. Okay, so this is an example of a directed graph. So this is a directed graph, okay? Now in this case, the way that we represent an edge is actually going to be with an, it's more suitable in this case to represent an edge with an ordered pair, right? With an undirected graph, it might be suitable, well, in my opinion anyway, it's more suitable to represent an edge with a set. But in this case, we really should, I think, represent edges with ordered pairs. So in a directed graph, we represent an edge, effectively, from I to j as an ordered pair. ij, okay? And the formal way that you would describe the graph, as we were talking about before, is still the same, right? You'd have the set of vertices and the set of vertices and the set of edges. But just going through an example, it'd be, so in this case, set of vertices we go from 1 to 6. So the set of nodes would just be the set of first 6 natural numbers, so 1, 2, 3, 4, 5, 6, like so. In this case, the set of edges, though, is going to be an ordered pair, right? And in this case, because we allow 2 edges, effectively between 2 nodes, the order matters, right? Because if I do an ordered pair like this, so if I say the ordered pair containing the element 1 first and then 2, I'm saying that's representing an arrow pointing from 1 to 2. Okay? And that's different from an arrow pointing from 2 to 1, okay? Because the arrows are pointing in different directions. And it doesn't necessarily need to be both in a graph. I could have just, I could just remove the arrow pointing from 2 to 1, and then I only have an arrow pointing from 1 to 2. Right? So, you know, we need, in this case, the order does matter. So it is definitely more suitable to use ordered pairs in this case. So we do have an arrow pointing from 1 to 2. We also have an arrow pointing from 2 to 1, so 2, 1 will also be there. Right? And what else do we have? We also have an arrow pointing from 6 to 3. So you're going to have sort of 6, 3. We have an arrow pointing from 6 to 1. An arrow pointing from, effectively, from 5 to 6. and from an arrow pointing from that should say 6, but there is also an arrow pointing from 5 to 4, so you can keep that. An arrow pointing from 5 to 6, and there's an arrow pointing from 1 to. Oh no, sorry, that wasn't the initial diagram. Okay, we can just add that in. I'll just add in an arrow from pointing from 1 to 5, so that becomes an ordered pair as well. So if I add in that, there's an arrow pointing from 1 to 5, and I also add in the ordered pair 1, 5. Okay, so there's going to be an arrow pointing from 1 to 5, and then that completes the set of all of my edges. Okay, so in this case, my edges are from 1 to 2, 2 to 1, 1 to 5, 6 to 1, 6 to 3, 5 to 4, and 5 to 6. Okay, so those are all my edges. So I have my set of vertices, my set of edges. Then I close off my my larger ordered pair, right, which starts over here and ends over here. Okay, and that now has specified my directed graph. Okay, and if it was an undirected graph, then both of these would be saying the same thing. So whenever you sort of include both of these like this, then that's sort of a hint at it being, well, that is really just telling you it's a directed graph, right? And also from context, people will normally say this is a directed graph. Okay, but if you just wanted to use sets, I guess in theory you could, for a undirected graph, just use sets in this set of edges here, right? Because the order doesn't matter. I to j is same as j to I. For a directed graph, to use ordered pairs, and then you can easily tell. But if they use ordered pairs in both cases, which is fine technically, then this sort of thing here would show you that it's directed. But you can still have a directed graph without necessarily arrows in both directions. So in that case, you wouldn't be able to tell, right? So probably easier then, if you wanted to avoid using words, to just use ordered pairs for directed and sets for unordered pairs for undirected to represent edges. But up to you, and also you could probably just infer from context anyway. So okay. So obviously we spoke about what it means to have a path for an undirected graph, which is just a sequence of nodes connected by edges, right? So you could go from 1 to 3 and then 3 to 4, right? So your sequence might be just like sort of a tuple 1, 3, 4, okay? Because there's an edge from 1 to 3 and an edge from 3 to 4. So then in that case, your path just goes from 1 to 4, so 1 to 3 and 3 to 4. That's a valid path. But we haven't really spoken about what it means to have a path in a directed graph, okay? So what does it mean, right? So we need to be clear about that. So a path in which all the arrows, right, point in the same direction as it steps, is called a directed path. Okay, so I mean, I guess actually, although I said that we didn't really define it for a directed graph, it is effectively the idea is the same fundamentally, right? That effectively a path is just a sequence of nodes connected by edges, effectively, and edges in this case just arrows, right? Well, I guess what I really meant is that we haven't really spoken about there are different types of paths for directed graphs, right? So for example, I could go from 2 to 1 and then 1 to 6, but actually in my directed graph, although that's technically a path, for my directed graph, that's not really sort of a legal path in a sense, because obviously there's no arrow pointing from 1 to 6. Okay, so what I really mean is that we haven't defined the directed path, which we say only works if it's a path where the arrows are always pointing in the same direction as the steps that you're taking. So if the sequence was 2, 1, 5, that would be a directed path, because 2 to 1, the arrow is pointing in that direction from 2 to 1, and then 1 to 5, the arrow is also pointing from 1 to 5. So that's fine. But 2, 1, 6 would be still technically a path, but it's not a directed path, okay, because the arrows are not pointing in the same direction, right? So from 1 to 6, the arrow is pointing against the way that you're trying to move. So it's not a directed path. So it's more just an undirected path, which is called a path in general. So that's what I meant when we say we haven't really defined it, because obviously there are different types of paths for directed graphs. One where you're stepping sort of against the arrows, and ones where you're moving with the arrows. The ones where you're moving with the arrows are called directed paths. Okay, and then I guess this is actually the last definition, I'm pretty sure. So we say that a directed graph is strongly connected, right? If a directed path connects every 2 nodes. So before we had connected, if it's just a path between any 2 nodes, so there's a way to get from one node to another, if you consider just any pair of node, and that's true for all pair of nodes in the graph. In this case, it has to specifically be a directed path. So you have to be moving with the arrows. Okay, so obviously it only applies for directed graphs, because otherwise you don't have arrows. But you could have a strongly connected directed graph if a directed path connects every 2 nodes. Okay, so I want to say that is the case for the graph I have up here, right? In other words, to get from 2 to 4 via a directed path, I could go from 2 to 1, 1 to 5, 5 to 4. I could get from 2 to 3 as well, 2 to 1, 1 to 5, 5 to 6, 6 to 3, and I think I can do that. Oh no, sorry, I can't, because I can't get from 3 to anything else. So that's not strongly connected, sorry, because I can't get from 3 to 2, for example. There's no way out of 3 that is a directed path. I go from 3 to 6, that's not a directed path, right? So that is actually not strongly connected. Okay, and a graph is strongly connected, just to recap, if for any pair of nodes that you take on your graph, there is a directed path between those nodes. Okay? Right, so the final thing I want to talk about is how we can visualize binary relations using graphs. So probably something that you might not have thought about too much, but we can use them. So directed graphs can be used to visualize binary relations. Okay, binary relations. Okay. If I have R, which is a relation, if R is a binary relation specifically, if R is a binary relation whose domain is the Cartesian product of some set D, okay, D cross D, okay, because remember that effectively relations are just functions, specifically binary relations are just functions whose domain is effectively going to be the Cartesian product of two of the same set, at least for the cases that we were looking at in the last video, and I think the cases they didn't talk about specific relations where the domain was the Cartesian product of two different sets for a binary relation. We only spoke about cases where the domain of the relation was effectively the Cartesian product of two of the same set. So that's what we have here as well, D cross D. Okay. So effectively, remember that binary relation is a function whose domain is the Cartesian product of two of the same sets, and whose effective range is going to be the set of the elements true and false. Okay. So effectively, you can take any of the ordered pairs within that sort of Cartesian product, and you can say that effectively the first element is related to the second element. If that's true, then the output will be true effectively. So that's how binary relation worked. So if R is a binary relation whose domain is effectively D cross D for some set D, so the Cartesian product of D with itself, okay, then a labeled graph. A labeled graph. Remember, a labeled graph is just a graph whose sort of nodes and or edges may be labeled. So labeled graph G, which obviously represent with the set of vertices, which in this case we say the set D, okay, the set of edges, which we still call the set E. So this specific graph defined via this, right, which obviously we need to specify the sets D and E to know which graph we're talking about. So that graph specifically will always represent our binary relation capital R. Okay, and then we also define E. So E is always going to be the set of all ordered pairs x, y such that x is related to y. Okay, or effectively remember this just means x, r, y equals true. So the output of the ordered pair effectively x, y is true. Okay, because remember it's a function. So if I have an ordered pair, x, y, and when I plug that into my function, what I get is the output true. Then we say that x is related to y. Okay, because all relations are functions. And in this case, the domain is going to be set of ordered pairs because it's a Cartesian product between two sets, so it's the same set. And obviously, the range is going to be either true or false. So in this case, if x are y, then the output will always be true for that specific ordered pair, effectively. Okay. So that's our set E, and this is the set of just of all our edges, effectively. Okay. So remember, we also use ordered pairs to represent edges. So effectively, we'll have connections between effectively the two nodes that effectively, when you put those the names of those nodes into an ordered pair, right? Then let's just look at the example because it's slightly convoluted for me to explain. But if we look at sort of one of the relations from the last video, then it looks something like this. So we had the beats relation. So we had it's for a game of rock paper scissors. So we had rock, scissors, and we also had paper, right? And as you remember, obviously scissors beats paper. So scissors, we say that the ordered pair, scissors, paper, right? Whenever you plug this into your function, the output you get is indeed true because scissors beats paper. That's the whole point of the relation. It just tells you what beats what, effectively. So because scissors beats paper, output's true. Then if we look at our set E, the set of edges is the set of all ordered pairs where x is related to y. So in our case, scissors is related to paper because when you plug that into the relation, you get an output of true. And so one of our edges will be effectively this, right? This exact ordered pair. And remember, in terms of graph theory, it just means that there is an arrow, and in terms of a directed graph, there's an arrow from scissors to paper, right? So that's where we start off. And then you repeat this, and obviously there'll be an arrow from paper to rock, and an arrow from rock to scissors because rock beats scissors. And this directed graph actually represents our entire relation because the arrows tell us which ordered pairs. So because it starts at scissors and ends at paper, that represents the ordered pair scissors, paper. And that tells us that scissors is related to paper via our relation, right? And then we also obviously know, so D is the set. So obviously the input to our relation is D, the Cartesian product of D with itself, because obviously remember that you're comparing effectively the first and second, sort of the first player's choice with the second player's choice, right? So for example, scissors, paper, this is one example of something that you might input into the relation, and that's an ordered pair. So you input the Cartesian product of two sets into the relation, but for the sake of the graph, the set of vertices is just D, right? So in our case, D is just the set scissors, paper, rock, set containing the elements scissors, paper, and rock, right? And so you can see that actually I've labeled my vertices accordingly, right? So one of my vertices is rock. Obviously, I didn't use capital letters, so that's technically wrong, but whatever. So obviously, one of my vertices is labeled rock, the other one is labeled scissors, the other one is labeled paper, okay? And so I can use my set D as effectively the set of nodes, the set of vertices in this case, right? Whereas D, the Cartesian product of D with itself will give me all possible ordered pairs, the first elements from D and the second elements from D, right? And then that is the input to my relation, okay? So yeah, effectively, this is the sort of graphical form of a relation, which you need to also be familiar with. So we're getting a little bit heavy, a little bit dense into some of the sort of connecting, we're bridging ideas that we've already covered at this point in time. And it's a little bit tricky to understand. It's quite tricky for me to explain as well. But hopefully you can see where I'm coming from. And if not, pause the video and then eventually, hopefully, you'll see what I mean. But effectively, because there's an arrow from scissors to paper, that's something that scissors is related to paper in my specific relation. Arrow from paper to rock means paper is related to rock. Arrow from rock to scissors means rock is related to scissors. And also the set of nodes is just the set containing the elements scissors, paper, and rock. And so that the Cartesian product of that set with itself gives me the set inputs to my relation. So I know everything about my relation just by looking at this graph. And I would be able to construct this graph by knowing about my relation as well. Even though I might not necessarily know what my relation is saying, that has to be explained effectively. But mathematically, the relation can be described using just sets effectively. And graphs, which are just sets effectively. Okay, so, right. That is going to be everything for this video. If you are a bit confused about the relation stuff at the end or anything in the video, do ask me a comment. Do send a comment through. But the relation stuff, I'd highly advise you check my previous video because I went through that stuff there as well. But anyway, without anything else to say, I think I'm going to end the video there. Thank you guys very much for watching. I'll see you guys in the next one. Goodbye.